Let's look at a couple of ways that we can use a gradient of a function of several variables. We can use any number of variables in our example, but we'll pick one function and work through several applications. First, remember that the magnitude of the gradient, or the opposite of that magnitude, records the maximum and minimum rates of change of f at a given point. Likewise, the gradient divided by its magnitude, the unit vector, or the opposite of that unit vector, records the directions in which we achieve these maximum and minimum rates of change of f at the given point. Remember that the gradient of f is always normal to level curves or surfaces, whatever number of variables we're using, whatever word is appropriate, created by the function f. And the gradient of f also helps us to find the directional derivative of the differential. You can think of that as the rate of change of f with respect to distance, or the amount of change estimated in f for a given amount of change estimated in distance. Let's look at the example for rate and direction of maximum change. So a function f of x, y, and z, a function of three variables, x, z plus y squared quantity over z cubed. And let's focus on the point 1, minus 1, and 1. The gradient of the function we can calculate. We can insert the point 1, minus 1, and 1. We have a vector 1, minus 2, and minus 5. The magnitude of that vector is root 30, about 5.477. That's the maximum rate of change of f at this point. And the direction in which that rate of change is achieved is the gradient divided by its magnitude, or 1 over root 30, 1 minus 2 minus 5. That's the unit vector that points in the direction in which f changes most rapidly. Look at another calculation, and let's compare creating a tangent plane to a level surface and a linearization. So f as a function of three variables, xz plus y squared over z cubed, at the point 1, minus 1, and 1. The value of the function at that point is 2, and this creates a level surface. The quantity xz plus y squared over z cubed equals 2. Now we already know the gradient of the function at this point, 1, minus 1, 1, is 1, negative 2, and negative 5. And this vector is normal to the level surface. So we can write the tangent plane with that normal. X minus 2y minus 5z, plug in the point that we know we're standing at, 1 minus 1 and 1. We get the value negative 2. So x minus 2y minus 5z equals negative 2 is the plane tangent to this level surface at this point. Now this is different from asking for the linear approximation of f at p naught. Remember, f is a function of three variables, so the linear approximation accounts for three rates of change. The value of the function at the point in question plus the differential. But I've already calculated the differential, the partial f, partial x, partial f, partial y, partial f, partial z. And so if I insert the values of x naught, y naught, and z naught, I have the function, the linear function, that approximates f best at the point 1, minus 1, and 1. And for example, if I wanted to estimate the value of f a short distance away from 1, minus 1, and 1, like 0.95 minus 1.02 and 1.1, I could plug these x, y, and z into the linearization that we just created and do the arithmetic, and I estimate that the value of the function will be 1.490. That's 2 minus 0.510. Let's look at the directional derivative differential. and verify that linear approximation in a different way. So again, the function xz plus y squared quantity over z cubed, and the point, base point 1 minus 1, 1, and a second point, 0.95 minus 1.02 and 1.1. The vector from P naught to P we can calculate. And we arrange things so we can calculate conveniently with integers. So the unit vector, which is the vector P naught P divided by its magnitude, is 1 over root 129 times negative 5, negative 210. So the directional derivative, the derivative of f in the direction of u at the point 1 minus 1, 1, is the gradient of f dotted with u. We can calculate minus 51 over the square root of 129. This is negative 4.490. It is the rate of change of f at p naught in the direction of u. Notice it's not quite as low as the minimum value of the rate of change of f, which was the opposite of the magnitude of f at this place. It's about 5.477 if we're remembering correctly, negative. But checking the differential, what happens if I move from P naught to P? As I did on the previous page. Well, notice that the df is gradient dot u times ds. And the little change in distance was the magnitude of P naught P. This cancels out the magnitude of P naught P from the unit vector. And so I'm taking the gradient dotted with P naught P, 1 minus 2 minus 5, dotted with 1 over 100 minus 5 minus 210. This is negative 51 over 100, or negative 0.510, exactly as we saw on the screen before. If you're curious, you can calculate the actual change in of f, delta f, from P naught to P. Remember, that's f of P minus f of P naught. And the actual change is negative 0.433. So slightly off right here by 77 1/1000ths from the actual change. Practice using the gradient in all of these contexts, particularly to create tangent objects to level curves, surfaces, or larger dimensional figures, and using the gradient in the directional derivative to calculate the differential.